In this video, I'll talk about calculating a Cohen's d effect size and what that means and why it's important. I've tried to emphasize that statistical significance doesn't tell you how big an effect is. Effect size tells you how big an effect is. Statistical significance is highly dependent on sample size, whereas effect size is not. Your book gives this sort of definition for a Cohen's d effect size: a difference between two means. Difference between, here it says, a predicted mean from one population and a mean of another known population divided by the population standard deviation, sigma. So this is the formula for how to calculate a Cohen's d effect size. It's just mean minus mean, so it's the difference between the two means divided by standard deviation. Really what this is doing is it's taking the difference between the two means. So it's trying to see how big is the difference between these two means in standard deviation units. So by dividing by the standard deviation, the number you get for the Cohen's d is the size of that difference in standard deviation sorts of units. So by doing this, you can compare the sizes of effects of different studies because you're putting them into standardized units, a standard deviation unit. One way to think about that is that sometimes people say that you can't compare apples and oranges, like you couldn't compare one study and another. This is bullshit. It's bullshit because a standard deviation puts it into a standardized unit where you can compare apples and oranges, so to speak. So a Cohen's d is one kind of effect size that tells you how big an effect is in a study. Mu1 is the mean for population 1, mu2 is the mean for population 2, which in the examples we've been talking about, it would also be the same as the mean of the comparison distribution, the mean for that distribution of means, because it's the same as the mean of population 2. Sigma is a population standard deviation. So in the z-test we've been talking about, this would be the known standard deviation from population 2. And that's going to be assumed to be the same standard deviation in both populations, at least in this case. When we talk about the Cohen's d in a later chapter, actually, there is actually a more complicated formula for determining what the standard deviation, how to calculate it with two different populations, but we're not there yet. Conceptually, this is always what a Cohen's d means, though. It's the size of the difference between the two means in standard deviation units. So to give an example, we've been talking about the personality attractiveness example. And this is actually a different mean than what we talked about previously. But again, to briefly refresh your memory, the idea is that one group of people is going to be told positive things about some people's personality characteristics, and then they're going to be asked to rate how attractive the person is. So imagine that the mean for the group that was told positive things about the people they're rating as personalities, let's say the mean attractiveness rating on some scale was 208, and then the known population for students who were not told anything about the personalities and just asked to rate how attractive the people were, let's say the mean attractiveness ratings given were 200. And we had said that the standard deviation was 48, so that's going to be assumed to be the standard deviation for both populations. So to calculate it, just like the formula above, it's pretty straightforward. 208 minus 200, so we get 8. And the standard deviation is 48, so we would just divide 8 divided by 48, and we get I think it's 167. So 0.167, so with rounding 0.17. So just to give you an idea of what this means, what if that difference between the means was larger? What if it was double the size? What if it went from 8 to 16, so it doubled in size? Well, what's going to happen with the Cohen's d? Well, if the standard deviation stays the same for 48 and the difference between the means doubles, then the Cohen's d is also going to double. So 16 divided by 48, and we get 0.33. So that's a doubling of the 0.17. But the reason you want to put it in a standardized unit is because a doubling of the size of the difference between two means doesn't mean anything doesn't necessarily mean that the size is double the size in a standardized way, Because what if your standard deviation was different? So in one kind of study, maybe the standard deviation is 48, but in a different kind of study, maybe it's half that. Maybe the standard deviation is only 24. Well, in that case, if we go back to the original mean difference of 8, but we have half the size standard deviation, a much smaller standard deviation, what's going to happen? We get a doubling of the size of the Cohen's d. So this 0.33 again is double compared to here, not because the size of the difference between the two means is double, but the size of that difference between the two means is double in a standardized unit based on numbers of standard deviations for whatever that research question is. So that's why the Cohen's d effect size is important, putting it into a standardized kind of way, because just a difference between two means can mean very different things in different contexts, in different sorts of studies. It depends on what the standard deviation, among individuals is. So just to visualize what we're talking about with an effect size, if we have two populations, if these two different distributions represent population 1, the dotted line is population 1, the solid line is population 2, that was our comparison distribution. So the dotted line, the population 1, again, those are the students that are experimentally told positive things about the people they're rating's personalities. Population 2 is the comparison distribution, students that were some known distribution where students are just not told anything about the personality, just asked to rate their let's say, physical attractiveness. And actually in the old study we saw we had a mean difference of 20, so it'd be 20, and again, the same assumed standard deviation of 48, and so we get a Cohen's d of 0.42 there. But if the mean difference was half that size, if it was only 210 for the mean of those told the positive characteristics, the Cohen's d would be 10 divided by, again, the same standard deviation of 48.21, so half the size in terms of effect size. So in terms of just kind of general conventions that have been accepted within psychology, it's been accepted that a Cohen's d of 0.2 or above, or slightly above, is a quote-unquote small effect. A Cohen's d of 0.5 up to 0.79 is a medium effect, and then a large effect in psychology is defined as a Cohen's d of 0.8 or above. Now, all of those numbers, even the one that is quote-unquote large, sounds relatively small. A Cohen's d of 0.8, that's less than one standard deviation above or below the population mean, or one of the population means. But just in terms of visualizing, again, a small effect is a smaller difference between the means of the two populations. A medium effect, it's a bigger difference, and a large effect is even larger. Now, again, don't confuse the size of the effect with statistical significance, because you could have a very small effect size, and if you have lots and lots of people, a very big sample size, even a much smaller effect than this 0.2 standard deviations can be quote-unquote statistically significant. Because again, statistical significance is really just telling you, do you have what you think is a reliable effect that's bigger than nothing? Effect size is telling you how big is it actually in the standardized sort of way. So in terms of what do the 0.2, the 0.5, and 0.8 mean, again, that a 0.2 is saying it's 0.2, the size of that difference between two means is 0.2 standard deviations. Even a 0.8 it's 0.8 standard deviations. So within psychology, to be honest, I'm not exactly sure where these conventions really came from, except for they were based on some, I'd say, limited studies in terms of what's common in psychology. And I'd say this does fit with kind of pretty typical findings in psychology. A lot of the effects in psychology, behavior and psychology are caused by multiple things. So any one factor in any one study is usually a relatively small effect. So even the 0.8 isn't really that big of an effect, but it's quote-unquote large but relative to studies in psychology. You could also use the Cohen's d formula and those conventions for a small, medium, or large effect for when you're planning a study. Ideally, when you're planning a study, you might be able to predict how big the effect size is. For example, maybe you have an idea of whether you think it's going to be a pretty small effect given your research question, or maybe it's a you think it's going to be a typical effect, so maybe you want to use the medium-sized Cohen's d, or maybe you think it's going to be a really large effect, or maybe you're only interested in something if it is a large effect. In that case, what you could do is use the Cohen's d formula in a different way. Let's say you plugged in the zero 0.5 for the medium effect size here, and let's say in this particular case you know something about some known population, so you know one of the population means and the standard deviation of it. With a little bit of algebra, you could solve for x for the predicted mean for population 1, and you could find out what is going to be the predicted mean if we think there's going to be a medium size effect. So you could multiply the Cohen's d of 0.5 if that's what you're expecting by the known population standard deviation, and then rearrange that to solve for x, and you can get an estimate of what the predicted mean for your research question is going to be. Alternatively, maybe you want to see how big your maybe there's a situation where you have a prediction about what the mean is going to be. Maybe you know the one population mean and you have a predicted mean, and you want to use this formula to get an estimate of how big do we think the effect size is going to be, so the predicted effect size. So there are questions like that in your practice problems. That's why I point that out. You're still going to be using the same Cohen's d formula to solve those.